All right, welcome back, everybody. Today we're going to be talking about section 8.1.1. And this chapter is going to be all about something new that we call factoring. So, factoring involves one of the ideas that we talked about back in chapter 3 with algebra tiles. So, in problem 8-1, we can see that we are just going to be reviewing what we know about products and sums. If you remember, product means multiplication and sum means addition. So in part A, it says write the area of a rectangle at the right as a product and as a sum. Remember, the product represents the area that's found by multiplying the length by the width, and the sum is the result of adding the areas inside. So when we look at this diagram, a couple of things that maybe should hopefully come to mind for us is our different algebra tiles. So we have a y tile right here. This is an xy tile. We have an x squared tile, and we have an x tile over here. And really, we have a bunch of other tiles over here that we can use kind of what we know about algebra tiles to sit there and figure out. So we know that this one must be a y tile, this must be a y tile, and this must be a y tile. Remember, the only tile that has the same length as an x tile is another x tile. These small ones over here are all of our unit tiles, so I can put a 1 by each of those. And then we get to these tiles in the middle. Now, remember, an x squared tile is x wide by x tall. So we know that these must, in fact, be x tiles. Now, one of the very first things they wanted us to do here was to write our expression as a sum. So if I wanted to write my expression as a sum, we would want to sit there and write out all the different tiles that we have. So it looks like we have one xy tile. It looks like we have 4 y tiles. Looks like we have 6 total x tiles. We have 1 x squared tile, and then we have 8 unit tiles. So this would be our area written as a sum. Now, aside from that, we also want to write our area as a product. Now, if you think all the way back to chapter 3 when we were first working with algebra tiles, in order to write our area as a product, what we did is we looked across the bottom and we said, what is the width of this big rectangle that we have right here? And we know that this is an XY tile, so this tile was Y wide, and this tile was X wide. And since both of these were just the short sides of the X tile, we know that that covered a distance of 2 because there was 2 of them. So our distance or length across the bottom here is Y plus X plus 2. Now we can do the same thing on the sides. So on the other side over here, when we try to measure it up, it looks like we had 1x down here, and then we had 4 unit tiles over here, which would tell us that this length is 4. So the length of this side would be x plus 4. So as a product, we would sit there and write that our area is y plus x plus 2, and we want to put parentheses around that, and then that's times x plus 4, right? The length times the width. And we know that the area written as a product and the area written as a sum are both going to be equal because of the fact they're both just representing the area of the rectangle. In part B, it says, use a generic rectangle to multiply 6x minus 1 and multiply that by 3x plus 2, and then to write your solution as a sum. So when we want to use a generic rectangle, remember this is a rectangle that is just one big rectangle broken into 4 sections. If this is the length, we could put that down on the bottom. So this would be 6x minus 1, and then this would be 3x and plus 2 here. Remember that in order to sit there and figure these out, we need to multiply the corresponding parts. So 3x times 6x, that's going to give us 18x squared. 3x times a negative 1, that's going to give us a negative 3x. 2 times 6x, that's going to give us 12x's. And lastly, 2 times negative 1 will give us a minus 2. Now, when we come over there, we want to write this out as a sum, is what we're being asked to do. Write your solution as a sum. So in order to write our solution as a sum, we want to take out each of those terms. So we have 18x squared, and then we have kind of something unique going on in the middle. So in the middle, notice how we have negative 3x's and 12x's. Those are like terms, so we want to sit there and combine them. So 12x take away 3x would leave us with 9x's. And then, of course, at the very end, we have the minus 2. So this would be our area written as a sum, and up above, you can see what our area was when it was written as a product. Hopefully, that helps refresh you a little bit. Now, the big idea of this chapter is going to be on what we call factoring. And what factoring is the process of changing a sum into a product. That is what we call factoring. And what it says here is it says, can every expression be factored? And I'll give you a hint on that one. The answer is going to be no. Not every expression is going to be factorable. Now, this is what I mean by factoring. So over here, we can see that we have an algebraic expression. And what we're supposed to be able to do is we're supposed to try to factor this. Now, the way we want to try to factor this is we're going to try to factor this by using algebra tiles. So I'm going to open up a web browser, and I want to go to the CPM algebra tiles. So I can type in CPM tiles. And when I do that and click on the first link, I will get to my CPM algebra tiles. Now, the process of factoring involves making rectangles. So what we're going to do is we're going to pick a background, and the background we're going to pick is the bottom one that says corner piece. Now, in order to use this background, what we're going to do is we're going to sit there and look at the expressions that we have over on the left. So over on the left, notice how we have 2x squared. So what that means is we want to go and grab 2x squared tiles. Notice how we have 7 x's. So remember, that just means grab 7 x tiles. 1, 2, 3, 4, 5, 6, and there's 7. And then last but not least, we have 6, which means 6 unit tiles. And it doesn't really matter where you put them right now, because we're going to be moving them all around. 1, 2, 3, 4, 5, 6. Wonderful. Now, once you have all of your tiles, what our goal is to make a rectangle with these. So as you may remember, you always want to start with your squared tiles. We're going to put those down here in the corner to start. And then what we're going to do is we're going to take all of the other tiles, and we're going to try to make a rectangle. Now, all of these are still making a rectangle here, so we don't have any issues. I'm going to purposefully do this one wrong because I want to remind you about some things with algebra tiles. So when I put 1 over here, 1 over here, and 1 over here, notice how we have that little bump at the very end. It doesn't match up perfectly because that does not make a rectangle. So we want to be a little bit more creative as we're moving these tiles around. So maybe let's try to take one of these X tiles. Remember, you can rotate them by tapping them twice. And maybe let's try to put a couple here. And when I do that, maybe I get a little bit closer here, but it looks like I'm still a little bit off. I have this extra tile over here that has nowhere to go. So let's try doing some other stuff. Maybe if I take another one of these and I put it up top here. Then look, all of the sudden I have an extra spot that opens up. Now, when we're looking at these tiles, one of the nice things about using this framework over here is that this framework can actually help us measure. So I'm going to grab a few more tiles here just to illustrate a point. 1, 2, 3. And then I'm going to grab another one here and another 2 over here. And I think you'll see in a second why I grabbed those tiles. Now, what I want to show you is that over here, notice how this distance, x plus 2, is how tall that rectangle actually is. And down on the bottom, that this rectangle, in terms of its width, is really 2 x's. Let me try to get that perfect for you. So we have 1 x there, another x there, and then we need 3 unit tiles to cover that same distance. So what that tells us about this is that tells us that this can in fact be factored. What factoring means is it's our ability to turn this number of tiles, right? So 2x squared, 7 x's, and 6 unit tiles. It's our ability to be able to turn those into a rectangle. And when something is factored, what we want to be able to do is we want to write that as a product. So we can see that the bottom length of our rectangle was really 2 x's plus 3 unit tiles. And the side width of our rectangle was really just 1x plus 2 unit tiles. Let's try to do another problem. So I believe I can clear my tiles, and let's try to do problem number 2. Now for problem number 2, I'm going to need 6 x squared tiles, so I'm going to throw them all out right now. Again, it doesn't matter where we put them. I'm going to need 7 x tiles, 1, 2, 3, 4, 5, 6, and 7. And then I'm going to need 2 unit tiles. And remember, our goal is to sit there and try to make a rectangle with these. So just like we did before, we're going to start with the x squared tiles, and we're going to put them in the corner over here. And with these, it's important to know you can kind of make these a couple of different ways. So if you don't get it the first time, definitely don't give up and keep playing around with it. So if I put all of my x tiles over here, those all fit really nicely over there. And then I could put this one up top here. But notice, if I put the ones where they match up, I'm missing an x tile there. So this did not make the rectangle I was looking for. So maybe let's try something else. So maybe I'm going to take another x tile, I'll put it over here, and then we still kind of have a problem because it looks like we're still missing a tile in order to make that work. So I'm going to just keep playing around with it and see what we can do. So I'll put another x here and another x here. And then maybe I'll actually move this one up, and then look at that. We actually were able to make a rectangle for this. Now, in terms of its length, it looks like this one was 3 x's tall, and then 2 units above it. And then on the side, it looks like this was an x, and then 1 unit tile in length. So when we come over here and we examine this, we would be able to say that this factored expression is really equal to, let's start with the bottom. So the bottom had 2 x's and 1 unit tile, and the side of this had 3 x's and 2 unit tiles. Very nice. Now I'm going to let you pause the video and go over those next 2 problems and see if you can find a way to factor those. Welcome back. Hopefully you were able to find a way to factor both of those 2 problems. And now we're going to kind of just keep moving on to 8-3. So it says, work with your team to find the sum and the product for the generic rectangles below. Are there any special strategies you discovered that can help you determine the dimensions of the rectangle? Be sure to share those strategies. Now, when I see a problem like this, these problems can really get a little tricky. And what you want to think about with these problems is I normally like to start with the simplest term. Actually, before we get too far into this, instead of just being 5x here, let's make this into 15x right down here. We're going to change the problem. I think there was a typo with the notes. Now, like I was saying, we always want to start with the simplest term. So I'm going to start with 5. And what we want to think about is we want to think about what 2 numbers do we know that multiply to give us 5. And I want to put those 2 numbers on the side. Now, I'm going to start by putting a 5 here and a 1 here, because I know that 1 times 5 is equal to 5. Now, there is a slight problem with that, because the next part of this, we would take 5 and we would say 5 times what is equal to 2x. And really, we're not exactly sure, because 5 doesn't go into 2x. So maybe I made a small mistake. So let's go back to the drawing board. Now, I chose to put 5 over here on the right, but I could have also put 5 up top. So if I move 5 up top, let's see if that makes any different changes. So now remember, 1 times something has to be equal to 2x. And hopefully you know that 1 times 2x is equal to 2x, right? Because if I were to multiply this times this, I should always get this. Nice job. Now, we want to keep going with that idea a little bit. So remember, 5 times what is going to be equal to 15x. Well, this one gets a little bit tougher, but hopefully you remember that 5 times 3x is going to be equal to 15x, because 5 times 3x equals this. Now, last but not least, this is kind of the fun part for me, is you get this spot where you get to check. So you want to say 3x times 2x, and you want to make sure that that equals 6x squared, which it does because 2 times 3 is equal to the 6, And since I had 1x here and 1x there, we have 2x's total. Nice job. So what we were able to do right there is we were able to take this generic rectangle and we were able to write it as a product. And when we write it as a product, we would have gotten 2x plus 5. And on the other side, I had 1 plus 3x. And what we just did is, since we took something that was already written as a sum and we turned it into a product, what we did is what we call factoring. And that's what this whole unit is going to be about. Let's do one more of those together, and then we'll save that last one for you to maybe try on your own. Now, when I look at this one, I'm going to start by looking at the simplest term, which again is just the one that's just a number. It doesn't have any variables. Not everyone's going to be set up this way, but if there is, that's the one I always like to start with. So when I look at this problem, what I want to think to myself is, what numbers multiply to give us 6? Well, I know that there's a couple of different combinations. 1 and 6 would be one combination. So if I put a 1 here and a 6 here, let's just check that to see if this works. Remember, if it works, then 6 times something should equal 2y. And since we don't know what that is right away, it's hard to make a big number smaller like that, we're going to say maybe we made a mistake. And we'll go back to the drawing board. It's okay to erase it and start over. Let's try to put a 1 here and a 6 here. Now, if I were to do it like this, we got to be kind of careful on this one, because this one had this extra negative sign. So we know one of our answers needs to be negative. So I'm going to put a negative there. Now remember, negative 1 times what would be equal to 2y? Well, negative 1 times a positive 2y would be equal to 2y. So right now, this box is good, and this box is good. Let's see if the bottom box works too. So 6 times what is equal to 15x? Well, that's where it gets a little bit tougher, because 6 times 2 is equal to 12, and 6 times 3 is equal to 18, and we never hit 15. So there's a problem here. So again, I'm going to go back to the drawing board and I'm going to restart. You can't be afraid to give up and restart. What other numbers multiply to give us 6? Well, what about a 3 and a 2? And let's make this one into a negative 2. So 3 times negative 2 gives us negative 6. This one works. Negative 2 times what would equal negative 2y? And hopefully you're able to see that negative 2 times y is equal to negative 2y. Let's see if the bottom ones work now. So 3 times what is equal to 15? And I know how to turn a 3 into 15. Remember, 3 times 5 is equal to 15. And since this one had an x, we know this must be 5x over here. Nice job. So now, when we're looking at this, we know the top left, the top right, and the bottom right boxes all work. Across the bottom, 5x times what is equal to 5xy? Well, 5x times y. So we know this bottom left box works as well. That's always the fun one, the last one. If you can get 3 of them to work, then the fourth one always works. Nice job. So we know that this factored would be y plus 3. I get that from the length of the top. And then negative 2 plus 5x, because that was the height of the rectangle. Very nice job. Now again, I want you to pause the video and I want you to try to work through this problem and see if you can come up with an answer. Remember, I would try to start up here in this box. All right, welcome back. Hopefully you had a chance to try this problem. I'm going to give you a hint. In case you didn't finish it, we should start with a negative 3 and a 4 here. And then I want you guys to try to finish the problem already. If you already found that those were those 2 answers, I'm guessing you were able to complete it correctly. If you didn't get those 2 starting numbers, then I want you to pause the video again and try to wrap up the problem. Hopefully, you were able to pause the video and go and attempt this problem on your own. And when you did, I hope that you were able to find that this is 3x plus 4 and negative 3 plus 4x as your factored form. Let's take a look at one last problem today. It says, while working on problem 8-3, Casey noticed a pattern with the diagonals of each of the generic rectangles. However, just before she shared her pattern, with the rest of the team, she was called out of class. The drawing on her paper looked like the diagram below. Can you figure out what these two diagonals have in common? So here's the first diagonal. Here's the second diagonal. And if we're looking at those diagonals, hopefully we notice something about them, and I can give you a hint. Hopefully you notice that there's something special that happens if I multiply the two diagonals together. So 6x squared times 5 and 2x times 15x. And if you notice, maybe let's do the bottom one first. So 2 times 15, that's going to give us 30. And then since I have 1x here and 1x there, we know that that's going to give us 30x squared. And then if I have 6 times 5, again, that's going to give us 30. And we know that we're going to get an x squared because this one had 2 x's. So look at this for a second. That's kind of cool. What do we notice? We notice that the diagonals, when they multiply together, that they give us the exact same answer. Let's go back to a problem. Let's try one of the other ones we did. Does that same pattern still work? How about this one? Actually, let's go to this problem. This one looks hard. So if I looked at the diagonals, what Casey thinks she discovered is that if she takes this diagonal, and if she takes this diagonal, and if she multiplies the diagonals, she says that we get the same answer. So let's just verify that to see if it works. So if I have negative 9x multiplied by 16x, that should give us the same answer as whatever 12x squared times negative 12 is. Now, I'm no genius. I'm going to use a calculator to help me out here. And I hope you would too. So if we have negative 9 times negative 16, we get 100. Ooh, hold on. Careful. I made a mistake. Negative 9 times a positive 16. I get negative 144. And then since this one had an x and this one had an x, we know that our answer will be x squared. Looking at the bottom one, if I take 12 times negative 12, oops, typed that in wrong, 12 times negative 12, I get negative 144. And since this one had two x's, we know our answer is going to have two x's. And look there for a second, notice how these two were both exactly the same. So it seems like Casey's pattern might work more often than it doesn't. Now, we're going to go and jump into the review preview. So if you're looking at the review preview, today you're going to be working on 8.1.1, and the problems you're going to be working on are 6, 7, 8, and 9. Now remember, if you are struggling with any of those problems, you should pop on over to Schoology and watch the homework help video. Thanks for watching, everybody. Have a good day.